Okay, we're going to start talking about Chapter 6, Ground Rules of Metabolism, because we are going to be focusing on A, how cells make energy, and B, how cells use the energy that they make to carry out the functions that they have to have. So this is Chapter 6 in your textbook. You can either watch this on YouTube or Facebook, or you can read about it in your book. It always helps to read in addition to doing the notes too. You should have your Unit 3 worksheet, Chapter 6, and you should answer these questions as you go. Okay, here we go. First of all, remember that energy is just chemical work. Cells need energy for metabolism. And remember, metabolism is just the sum of all chemical reactions in the body. Okay, there are a couple of laws of thermodynamics that we want to talk about that you probably talked about in physics before. Remember, the first law of thermodynamics says that energy cannot be created or destroyed. It can only be changed from one form to another. What are some different forms of energy that you talked about in other classes that you've had? Remember that energy of motion is like kinetic energy. Stored energy is potential energy, and that can be in the form of chemical bonds. We also talked about how there's thermal energy, which is the energy of heat, mechanical energy, which is the energy of movement. So there are lots of different forms of energy, and we never lose energy. We only change from one form to another. The second law of thermodynamics says that energy tends to spread out or disperse spontaneously from concentrated to less concentrated forms, such as dispersed as heat. This also can be called the law of entropy. And entropy is kind of a difficult topic to understand, but it's a measure of how much and how far a concentrated form of energy has been dispersed. There's a little mistake right there. This should be form. Sorry for the messy writing. Entropy is a measure of the disorder that systems tend to head toward. Hold on just a second. Everything in the universe, it tends to head toward a state of disorder. That's what entropy is. Okay, here you go is a drawing of the difference between endergonic and exergonic reactions. We're going to talk about those in a second. I'll come back to that. Okay, let's talk about the one-way flow of energy. So far you should have answered through question 6. So the question is, what resists the spontaneous direction of energy flow? In other words, what in your body resists this tendency for things to head toward a state of disorder? So it says everything heads toward disorder, but the strength of chemical bonds in your body resists the spontaneous direction of energy flow. So although things naturally tend to head toward disorder, there are chemical bonds in all things that tend to resist the spontaneous direction of energy flow. It says, how do systems maintain their organization? It's because you're constantly being resupplied with energy. All organisms are. That's why you eat. Okay, and then it talks about here, what is the original source of all energy, of almost all energy? It's the sun. And if you remember from Biology 1, we talked a little bit about how there were a few autotrophs or producers that still made their own energy, but they use chemicals like sulfur instead of the sun. And remember that was called chemosynthesis, and those are things like archaebacteria and things that live in extreme environments. Okay, so that gets us through number 9. Let's talk about metabolism for a second. Again, let me remind you that metabolism is supposed to be the sum of all chemical reactions in the body. The question here says, what are the key players in metabolism? In other words, what are the most important factors in an organism's body that are going to affect metabolism? So it says the key players in metabolism are reactants, products, enzymes, cofactors, energy carriers, and transporters. If you'll remember, a reactant is, what the substances that enter a chemical reaction. Products are the substances that are produced by a chemical reaction. We're going to talk about enzymes in a few minutes, but if you'll remember that enzymes are actually substances that speed up the rate of chemical reactions. Cofactors are things like vitamins that help an enzyme do its job. And then we have energy carriers and transporters. Number 11 says, what is activation energy? It says all reactants require a minimum amount of internal energy before they will enter a reaction, or activation energy. So activation energy is really just the amount of energy that it takes to get a reaction started. The lower the activation energy, the easier it is for a reaction to occur. So the job of an enzyme and many other things is to lower the amount of activation energy that you need, because we want to make things easier instead of more difficult. Okay, and then if you'll turn over and flip to the back, it says to distinguish between endergonic and exergonic reactions and give examples of each. These mean exactly what they look like they mean. Ender means inside or absorbed. Exer means it's going to be released. Okay, so it says some reactions are endergonic. And what that means is that they require a net energy input to run to completion. Photosynthesis is an example of this. So you take the energy from the sunlight and the energy goes into those chemical reactions in plants and allows plants to produce sugar. That is an endergonic reaction. On the other hand, some reactions are exergonic. And those are reactions where the net amount of energy, hold on just a second, the net amount of energy they release is greater than the amount of invested. So actually there is a release of energy in an exergonic reaction. And the example here is cellular respiration, which we'll be talking about more here in a few days. That releases energy. If you remember, photosynthesis and cellular respiration are opposite processes of each other. In a photosynthesis, we are going to make glucose. And in cellular respiration, that's the process where we break down glucose to get energy from it. And remember, energy is just ATP, and this happens in the mitochondria of the cells. Okay? It says cells couple reactions that require energy with reactions that release energy. So what that means is that your cells naturally will couple reactions, one that requires energy and one that releases energy, so they can work together to carry out the function that the organisms need. So that actually answers number 13. What types of reactions do cells couple together? Ones that require energy and ones that release energy. All right. Moving on, let's talk about ATP. And you can see that I had, I don't know what happened to the P there, but when I think of ATP, I remember a few of you didn't know exactly what that meant at the beginning of the semester, but ATP is just energy. I've described as wallet being energy. Well, let me back up. Sorry about that. ATP would be the energy, and if you compare that to a wallet carries money, and ATP is the molecule that your energy is carried in, if that makes any sense. So it says ATP is the currency in the cell's economy. It does a lot of work for your body. So we're actually on number 14. What is phosphorylation? And that is actually when you break down ATP to get energy from it. So let's move here. This right here, I'm pointing to this right here. This is an ATP molecule. Okay? This is what ATP looks like. It stands for adenosine triphosphate. Let's move that out of the way. And as you can see from this reaction, if I have ATP and I remove here, if I remove one phosphate group, it becomes ADP. And when I remove one phosphate group from ATP to create ADP, that actually releases energy. If you'll look here, it says structure of ATP, adenosine triphosphate, because there's 3 phosphate groups. And then here, we're going from ATP to ADP. And now there's only 2 phosphate groups. And that whole process releases energy, and that is called phosphorylation. Okay? I hope that I'm making some sense here. You have to bear with me. This is the first time that I have done a presentation like this. This is just another diagram of showing you what phosphorylation is. And it actually shows you how much energy is being created. Take a moment to look at that diagram and kind of figure out what's going on. It says, let's look at this A. It says glutamic acid paired with an ammonia, and that adds 3.4 kilocalories per molecule of energy. But if you add ATP, look what you get there. Okay? Okay, so and here's this process again. If we take ATP and turn it into ADP, then it actually creates energy. See if there's anything behind here that you need to know. Okay, I really hope that you've been getting this sound. Okay, it says, did you know that 107 molecules of ATP are used and then regenerated per second per cell? That's crazy considering that you have trillions of cells. All right, let's move on to something I feel like you're a little bit more familiar with. Let's talk about enzymes. We are